So experimental determination of rate equations. So we'll look at two different methods. One is the isolation method. And let's look at how we could use the isolation method, and we could use it in concert with integrated rate laws. So what we can do is imagine we have a reaction A and B going to C. So let's say we've got A plus B going to C, and we don't know if it's first or second order or zeroth order in A and B. So one way we could do this is to look at what the integrated rate equation is for this. Now, it's a little bit difficult since we have two reactants. So one thing we can do is we can break this into steps. So first, we'll run, and this works especially well, of course, if one of these, or if these are liquids, but we can do it even if they're not liquids. You run in a vast excess of A. Okay, so if there's a vast excess of A, the concentration of A is not going to change during the run. Okay, so we're going to use up all our B. Well, we still have tons of A left over. So really what we're doing is we're looking at the effect of the concentration of B changing. And so when we do this, remember the whole point here is to find a rate equation. So we're trying to find those exponents, alpha and beta. So when we run it in a excess of A, we can see that since the concentration of A is not going to change during the run, all of this is going to be constant, right? Because this is not going to change. So what we find is that V is going to be equal to some K observed times the concentration of B to beta. And what we could do if we wanted to was graph this and see, oh look, it's, for instance, if it were a log concentration versus time graph, then we'd say, oh, well then it's first order in B. So imagine we do this and we find that beta is equal to 1. Okay, great. And this is because we graphed the log of concentration of A versus time. And we got something like that. Okay, so now we know that beta is equal to 1. So now we run the reaction with a vast excess of B. So maybe we put in 100 times as much B as we do A. And so the A is going to be depleted rapidly during the course of the reaction. The B will be remained virtually unchanged. And so in this case, we're finding V, and this, of course, K observed, we'll call it K observed prime because it will be a different number. We'll be finding how the concentration of A affects the rate. So, for instance, let's imagine that we graph and we find that 1 over A naught, or 1 over A gives us a straight line. Well, then we know it's second order in A, and so we can say that alpha is equal to 2. And then we can put everything together and say the actual full rate law would be concentration of A squared times the concentration of B. That's the isolation method. So notice over here we said it was first order. Because it was first order because we swamped it with A, so we weren't really probing the effect of A, we call this reaction pseudo-second. Pseudo-second order. And this reaction down here, because we swamped it with B, we're only looking at the effect of A, this one up here is pseudo first order. This one down here would be pseudo second order. Okay, so basically when you swamp it with one component, you're just probing the effect of the other, so it's going to be pseudo in whatever order that component is. So if you're using a ton of A, this reaction would be pseudo first order. If we use a ton of B, the reaction would be pseudo second order. In practice, this method does not work all that well because if you run to long reaction times, you tend to get side reactions. There's always the possibility that the reaction will begin to equilibrate, so we've got back reaction. And so we're going to actually turn more often to the second technique, which I'll show you in a second. And that technique is a technique of initial rates. And with the initial rate data, you don't allow the reaction to progress very far, and so you don't have to worry about side reactions. So you might run, if a reaction had a half-life of an hour, you might only run the reaction for 5 minutes. And so what that means is that instead of trying to find this, where the concentrations are going to be variables that are going down over time, you're finding this instead. You're finding how the initial rate varies with the initial concentration. And that means that the only variables in the equation are the exponents. And this makes life much easier. So what we can do with this equation is take the log of it. The log of V naught is equal to the log of K plus the log of A naught to the alpha plus the log of B naught to the beta. Because remember, the sum of a logarithm is the logarithm of the product. Great. Now what we can do is remember the product. A useful property of logarithms is that we can pop these in front of the logarithm, these exponents. And so this is equal to the log of K plus alpha log of A naught plus beta log of B naught. And that allows us then to probe the kinetics by holding one of those numbers constant and varying the other. So what we might do is do an experiment where we're going to hold the concentration, the initial concentration of A constant. But we're going to vary B naught. Well, if you do that, you could do a plot where you're going to plot, let's plot this over here. Let's go ahead and plot the log of B naught, since the concentration of B is what we're, the initial concentration of B is what we're varying. And on this axis, we'll plot the log of the initial rate. If we do that, we can see we've used this as our x. And this, oops, let's write it again, as our y. Well, that'll be a straight line if everything else is constant. Well, the rate constant's constant because we're not changing the temperature. We didn't vary A naught, so this is a constant, so we could call this entire collection of constants the y-intercept B. And the order of the reaction in B is a constant as well, so that'll be the slope. So now we have y equals mx plus b, and we can see the slope of the line that we get is going to be the order in B. And the y-intercept is going to be the log of the rate constant plus the order in A times the log of A naught. So if we look at this, we're going to get a bunch of points when we do this. And so the slope of that line is equal to beta. So then we could do a separate experiment where we did just the reversed, where we varied A naught and held B naught constant, and we could get the rate from that, or we could get the order in A from that. Let's do a quick example. Let's have some initial rate data. And this is going to be either rate data is going to be in concentration per time. Sometimes the concentration units will be in millimolar, so we'll do millimolar per second. Got A naught in millimolar and B naught in millimolar. And finally, we're going to have the log of the reaction rate as the y, and the x is going to be the log of A naught. So we've got 3 experiments where B isn't changing. Now in this case it doesn't really matter because we're 0 order in B, but in some other cases it's not 0 order, so we want to pick ones where these are all constants. We pick these, they're all constant, and then we look at the corresponding A naughts and the corresponding reaction rates. And we take the log of those. We get the log of A naught first. We'll take the logs and we get 4.6, 5.3, 5.7. And the log of the rate, we get 2.3, 2.6, and 2.8. When we graph this, we see that we get a graph that's linear. And we get the slope. And the slope is actually equal to 0.48. So looking at this, we can say, oh, okay, that's essentially a half. So now we can write the rate equation. V is equal to K, A to the 1/2. So it's half order in A and 0 order in B, and half order overall. So this method is especially useful when we've got data that maybe we can't really pick out what the rate law is by inspection because maybe not everything is going to be an integer multiple.